Okay, so we need to do this last example in the trigonometric substitution section. So this was a problem. This one's different from the others because this is a definite integral, so we're going to have to deal with the endpoints. Again, you should run through your little checklist. Is it straight integration? Probably not. What about a substitution? The logical substitution is u is x squared minus 3, du is 2x. You don't have a 2x waiting for you. It's certainly not a trigonometric integral. There's no trig function in it. It's certainly not partial fractions because it's not a rational function because the exponent's not an integer here, it's 3/2. And integration by parts, maybe. But the expression here is so complicated that it's not looking very promising either. But why is it a problem in this section on the trig substitution? Okay, don't let the 3/2 throw you. Remember, 3/2 power means, well, if you have y to the 3/2 power, remember the 3 is power and the 2 is root. So this is either, you can either take the power first or the root. So this is either take the power first, y cubed, and take the square root, or you can take the square root of y and then raise it to the power. Either way is fine. Right? If you think of this in terms of this context, think of this as a root to a power. Notice what this is, x squared minus 3 to the 3/2 is the square root of x squared minus 3 all cubed. Okay, so now you can see it fits this section because it's the square root of something, a variable square minus a constant. Okay, so don't let the 3 throw you. It's the square root that kind of puts it in this section. Even though you can do trigonometric substitutions and problems that don't have roots at all, but don't let the 3/2 throw you. It's because it's a square root here. Okay, so that's how I'm sort of thinking about this. So I'm thinking of a square root of x squared minus 3. Okay, but then the whole thing cubed. Okay, so what about a trig substitution here? So what are we going to let x be here? Okay, so there's two things to ask yourself. What coefficient do we need and what trig function do we need? It's variable square minus a number, so remember that's secant. Because when you want secant squared theta minus 1. And now what coefficient do we need? I want to be able to factor out this 3, so I need a 3 when I square the x. So you're going to need square root of 3. Okay, and then dx, if you're not sure why it's root 3, you'll see when we get going. That's square root of 3 secant theta tan theta d theta. The derivative of secant theta, tan theta. Okay. Okay, so let's do the substitution. Again, do the dx stuff first. So that's square root of 3 secant theta tan theta d theta. I'm going to have 1 over. I think I'm going to rewrite this like I did a second ago with the square root and the cubed. So it's the whole thing cubed. So I'm pulling off that 3. And then we have the square root of the x squared minus 3. Okay? So then x squared is 3 secant squared. 3 secant squared minus 3. So I'm rewriting this 3/2 power as square root of something cubed. All right, let me check my work here. So there's dx, right? 1 over, the cube is here, the square root is here, and when I replace x with root 3 secant theta, that becomes, when I square, you get 3 secant squared theta minus 3. Okay, now, be careful here. What I've written here is not technically true because I have a definite integral equals an indefinite integral. Again, I like to change the endpoints. Again, you don't have to change the endpoints, but don't write -2 and minus root 6 here. That is not a true statement. These are endpoints for x. If you like going back to the original variable and using the original endpoints, don't leave me hanging. Just put an a and a b. And then when you go back to x's, you can write the -2 and the minus root 6. But I want to change the endpoints. Especially when you saw, remember in the other examples we did, when going back to x took a lot of work. Okay, now this is going to take a lot of work to change the endpoints too, but okay, so before we move on and start simplifying, I'm going to go ahead and change the endpoints. So remember, this is x and this is x, okay, and we're trying to figure out theta. So let me do the minus root 6 first. So I'm letting that be x, and I need to figure out the value for theta for my theta integral. So I'm putting minus root 6 in for x. Minus root 6 is root 3 secant theta. So secant theta is minus root 6 divided by root 3, but a root divided by a root is a root of a quotient, so that's just minus root 2. So we have to find the theta here. All right, now again, we're going to do the assumption, like we mentioned on the other examples. We're assuming theta is in the same, the value of theta is in the same range of values that the inverse trig function secant inverse has. Now, where does secant inverse live? Remember, secant inverse is from 0 to pi. So when I find theta here, I'm trying to find the theta from 0 to pi that makes this true. Okay, so, well, if secant theta is negative root 2, we're not in the first quadrant. So theta has to be in the second quadrant, so I'm going to draw it that way. This is not to scale, of course. So here's my theta in the second quadrant. And secant is minus root 2. Again, if you think of that as being over 1, and what's secant is the hypotenuse over the adjacent. Now remember, the hypotenuse is never negative. So even though I wrote the negative on the root 2, it's really on the 1. So the hypotenuse is root 2, and the adjacent side, x value is negative 1. I'm not saying the length is 1, I'm saying x is negative 1. Well, you know from your pre-calc class that this is one of your special triangles. If a leg is 1, the hypotenuse, in a right triangle, if the leg is 1, the hypotenuse is root 2, the other side's 1. You could check with the Pythagorean theorem. 1 squared plus 1 squared is root 2 squared. Now we're trying to find theta, but first you find the reference angle. You should know from pre-cal, in a right triangle with two legs being the same, that's your 45, 45, 90 triangle. Again, we're in calculus, so we're using radians, so that's pi over 4. Now that's not theta, that's the reference angle. So what's theta here? Well, from here to here is pi. If you back up pi over 4, that'll tell you theta. So it's pi minus pi over 4, which is 3 pi over 4. Okay. So the reference angle is pi over 4 radians. So from here to here is 3 pi over 4. So that's a little work. So the negative root 6 becomes 3 pi over 4. Now we have to do the same thing for negative 2. So let me get rid of this. Okay, if you need to pause the video, go ahead and pause and copy this down, but I'm going to erase it. Okay, so now I'm assuming that x is negative 2, so I'm putting negative 2 in for x. If I divide both sides by root 3, I get minus 2 over root 3. So there's secant theta. Again, I'm going to assume that theta is in the same range of values for the secant inverse function. So again, 0 to pi. And once again, secant is negative. Secant is negative. And so we're going to be in the second quadrant again. Again, I know my triangle looks the same, but it's a different triangle. And again, think of this as 2 over negative root 3, because r is not negative. So the hypotenuse is 2, and the adjacent side is x is minus root 3. And again, if you know your special triangles from pre-cal, if you have a right triangle with a hypotenuse of 2 and a leg of root 3, the other side is 1. Your 1, 2 square root of 3. And you should know this is your 30, 60, 90 triangle. Here's your 90. So one of these is 30 degrees, one of these is 60. The smallest angle is always opposite the smallest side. 1 is the smallest side, so 30 degrees is here, your reference angle, which is pi over 6. Again, if you were rusty on your special triangles, your 30, 60, 90, your 45, 45, 90 triangle, go and look in, go get a pre-cal book. Go to Amazon, find an old edition of a pre-cal book. It's not like pre-calculus has changed in the last few years. You can find an old edition of a decent pre-cal book for a couple bucks. All right, so you can buy one and have it in your library of books. Okay, but that's not theta. That's the reference angle. So theta is the angle from here to here. So it's pi all the way to here minus pi over 6, which is 5 pi over 6. So that's the lower limit here, 5 pi over 6. Notice 5 pi over 6 is larger than 3 pi over 4. So if that bothers you, remember you can switch the endpoints and put a negative sign out front, but I'm just going to leave it. Okay, so that was a lot of work to change the endpoints. but I wanted to review some trig. So that didn't hurt. Okay, now we can keep going with our definite integral here. We need to clean this up. But again, I'm not going to go back to x's. I don't need to anymore. So, what do we have here? Well, nothing cancels out right away, so I'm just going to take my time here. Secant theta, tan theta, d theta. I'm putting this in the numerator. And then I'm not worried about the cube yet. Remember, what we want to do is factor a 3 under the radical. So it's a square root of 3 times secant squared theta minus 1. So all I did in that step was factor out a 3. That's all I did. Okay. Let me save myself some room here. I don't think I need the dx. I don't think I need this anymore. I think I'm going to leave this just in case I need it. Okay, now I have a little bit of room. Okay, so let's continue here. I could have pulled the root 3 out front. So I'll do that. I'm going to pull the root 3 out front. Again, write complete steps, please. I still have a secant tangent in the numerator. And the d theta out here. Okay, now we have to be careful here. Again, I'm not worried about the cubes, well, so much. Let's just focus on the constant first. So I have a product here, so I can break up the radical. So this gives me a root 3. But remember, we're cubing as well. So this is root 3 cubed. That I can pull out front. Root 3 cubed. See, before we just pulled out a root 3, but there was no cube here. So this is, break that up. That's root 3 times root of that. Root 3 cubed is what I put out front. And notice here we still have, okay, till that's gone, we have square root of secant squared theta minus 1, and secant squared theta minus 1 is tan squared. Okay, so that's where we are. Okay, so I'll continue over here. So we have a root 3 and a root 3 squared, so one of the root 3's cancel. You're left with a root 3 squared in the denominator, so it's 1 over 3. Root 3 squared is 3. Okay, so that's good. Then we still have the 3 pi over 4, 5 pi over 6. Okay. Now let's do some simplifying here. We have secant theta, tan theta. Okay, now, and we still have the cube here. Okay, we have to be careful. Remember when we had the indefinite integral, we said, oh, the square root of tan squared is tan. Okay, even though we had that issue, when you let x be secant in the trig substitution, remember the tangent was fishy. But we have a definite integral here, so we can actually be careful. Okay, let's look at the square root of tan squared, right? We talked about this before. The square root of tan squared is absolute value of tan. Right? Right? And the question was, well, is theta in the first quadrant or is theta in the second quadrant? Because tangent's positive in the first and negative in the second. So you can't just drop the absolute value bars like we did when we let the trig substitution have sine or tangent, right? That wasn't an issue. However, we have a definite integral here. We are running from 5 pi over 6 to 3 pi over 4. Remember the picture we had before. Both of those angles are in the second quadrant. So this integral is ranging over values from an angle in the second quadrant to another angle in the second quadrant. Theta's in the second quadrant. I know theta's in the second quadrant. In the indefinite integral, we didn't know, and we just kind of ignored it. Theta's in the second quadrant. In the second quadrant, tangent is negative. So I can't just drop the absolute value bars, okay? Because tangent's not positive. But we talked about in class, remember, if the square root of y squared, if y is less than 0, you can rewrite that as negative y. Right? Because remember, the absolute value, the absolute value has to be non-negative, right? So the absolute value of y squared, that's not what I mean. Let's try that again. What I mean is absolute value of y. Sorry. Okay. So if y is positive, the absolute value of y is y. If y is 0, the absolute value of y is y. But if y is negative, the absolute value of y is negative y, because that'd be a negative negative, which would make it positive. Okay. Now here I know that in the right theta's in the second quadrant, so tan of theta is negative, and the absolute value of a negative number is the negative of the expression in the absolute value. So for this particular problem, because theta's in the second quadrant, I know tangent is negative, therefore this is going to be negative tan theta. Now, what if, hypothetically, what if my limits of integration were, pi over 2 to 3 pi over 4? No, it's pi over 4 to 3 pi over 4. Pi over 4 is in the first quadrant, where tangent's positive. 3 pi over 4 is in the second quadrant, where tan is negative. What you would have to do is break the integral up. So what I'm saying is, if this were pi over 4 to 3 pi over 4 of this, you'd have to break that up from pi over 4 to pi over 2, right? So first quadrant of whatever, plus the integral from pi over 2 to 3 pi over 4. That'd be from here to here. So notice this one, your theta's in the first quadrant, so the absolute value of tan theta would be tan theta. On this one, you'd be in the second quadrant, you'd replace the absolute value of tan theta with negative tan theta. So you have to do it as two separate integrals. But we don't have to do that here, because theta is always in the second quadrant, so tangent is always negative in this problem. So that's what we're going to do. So instead of the square root of tan squared, right, that's the same thing as absolute value of tan theta, which is minus tan. Okay. So we can't just ignore and say, oh, square root of tan theta, square root of tan squared theta is tan theta. We can't do that like we did on the indefinite integral problems, because I know theta's in the second quadrant, which means tangent's negative. Now we can go ahead and continue with the simplifying. So we had to stop and be careful on this one. Okay. If my limits of integration here had been in the first quadrant, 0 to pi over 4, I would have just said square root of tan squared theta is tan theta. Okay, so now what do we do? Negative 1 cubed is negative 1, so I can pull that out front. And then I have secant theta. I have a tan theta. And then here I'm going to, the negative over, that's going to be a tan squared. So I'm going to have a tan over a tan squared. Tan cubed. I'm going to have a tangent over a tan cubed, so one of them cancels, and you get tangent squared. Let me check myself. So negative 1 cubed is negative 1. I pulled that out front. I'm going to have a tangent cubed in the denominator, but you can cancel one of the tans with one of the tans in the tangent cubed. That gives me a tangent squared. Okay, so that's where we are. Now be careful. The derivative of tangent is secant squared. So, if this had been secant squared over tan, I'd let u be tangent, and then you'd have the du. But that's not what's going on here. Notice this doesn't really fit the format of our rules in the trigonometric integrals section. So what do you do with this mess? Well, I think I would change everything to sines and cosines and see what we get. Yeah, that's a strategy that sometimes works. So I have negative 1/3. Integral of 5 pi over 6, 3 pi over 4. Secant is 1 over cosine theta. And then tangent squared is sine squared theta over cosine squared theta. So I'm just recopying everything. Write out complete steps. Okay, so if I invert multiply, I'm going to have cosine squared over sine squared, and you can cancel one of the cosines. So I'm going to get cosine theta over sine squared theta. Right? If you invert multiply, you're going to have cosine squared in the numerator. That cancels with the cosine. You still have a cosine numerator, and then sine squared in the denominator. Now, we still have the same situation that we had here, right? The derivative of sine is cosine. Oh, well, so there we go. Or, I mean, yeah, there's no need to do a substitution here. I was going to do something different, but I noticed if you let u be sine theta, du is cosine theta. There's a good u substitution. But you don't actually have to do that here, because you can rewrite this. It'll save you a step, so you don't have to do a substitution. If you break this up as cosine over sine times 1 over sine, right? Cosine over sine is cotan theta, and then 1 over sine is cosecant theta. So if you do some rewriting, you see what I'm doing? I'm breaking this up as cosine over sine times 1 over sine. That's what I'm doing. And cosine over sine is cotan, 1 over sine is cosecant. And notice we can integrate that. Okay? So if you realize that, you don't have to do a substitution. That's a standard trick. When you change things to sines and cosines and you get a square or a different power, break it up like I did, right? Cosine over sine is cotan, 1 over sine is cosecant. That's a standard thing, to break that up somehow. Okay? So we know the integral of cosecant theta, cotan theta, right? It's minus cosecant. So minus cosecant, I'm going to pull the minus out, now I have a third. Cosecant theta evaluated from 5 pi over 6 to 3 pi over 4. Again, I don't have to go back to x's because I already did change the endpoints. Okay, so now we can just plug in the endpoints. I don't need this anymore. Right, we're using fundamental theorem of calculus here. We found an antiderivative, and now we're plugging in the endpoints and subtract. So it's 1/3 cosecant of, again, plug in the upper limit even though it's smaller. Always plug in the upper limit first. Minus 1/3 cosecant of 5 pi over 6. Okay. Now, if you look back at the triangle pictures I had earlier, I'll go ahead and redraw them, I guess. I mean, we already have the picture for 3 pi over 4 and 5 pi over 6, so just refer back to those. So 3 pi over 4, remember, was here. 3 pi over 4, reference angle pi over 4, and it's your 1 square root of 2 with a negative on the x, because in the second quadrant, x is negative, y is positive. So looking at this triangle picture, what's the cosecant of 3 pi over 4? It's the hypotenuse over the opposite. Right? Cosecant is hypotenuse over opposite. Remember, we say opposite, it's not opposite that angle, it's opposite the reference angle. So it's square root of 2 over 1, which is square root of 2. Square root of 2 over 1. And for 5 pi over 6, again, just look back at the triangle picture I already had for that one. It's 5 pi over 6. The reference angle is pi over 6. That's your 30, 60, 90. The numbers are 1, 2 square root of 3 on this triangle. It's 1, 1 square root of 2 on this one, 1, 2 square root of 3. And remember, largest side has to be the hypotenuse, so 2 is the biggest number, so it's on the hypotenuse. And of these remaining numbers, 1 is the smaller of the two, which means it's opposite the smallest angle. That's your 30 degrees, that's your 60. So it's 1 here and minus root 3. So this is the same triangle we had before. Okay, so what's the cosecant of this? It's hypotenuse over opposite 2. So it looks like I'm getting square root of 2 minus 2 over 3. And that's the answer. Okay, so hopefully this one wasn't too bad. The only new thing was the changing of the endpoints. And realizing the angle theta here, the range of the values, and from 3 pi over 4 to 5 pi over 6 was in the second quadrant. Theta's in the second quadrant, tangent's negative, so the square root of tangent squared turned out to be negative tangent, so that was a little different too.